Yeah, so my presentation today will be on the revision to 8500. I'm going to look at some of the main changes, how they may be implemented within industry, and some points that you should just consider when specifying concrete to the revision. So first of all, if we consider where the specifications for concrete sit within the hierarchy of standards. I mean, at the very top, we have national building legislation and building regulations in place of use, and underneath that is the basis of structural design. Beneath that, we have the codes for execution, design of concrete structures, and precast concrete. And EN 206 and, by extension, BS 8500 sit within that layer feeding into Eurocode 2. Now, beneath EN 206, we have a further suite of standards. On the left-hand side, we have those for the constituent materials, and on the right-hand side we have the standards for assessing concrete, both plastic and hardened. And I think it's key to note here that we're asked regularly why we can't include all sort of novel materials into concrete. And the reason is that the standards that feed into EN 206 that tell us what the constituent materials are all designated for concrete. So they are admixtures for concrete, they're pigments for concrete. We can't simply add anything that isn't already standardised for the use in concrete into this suite of standards. Now, EN 206, it's a non-harmonised standard, and so what that does is it allows complementary standards for provisions in place of use. Now, in Ireland, for example, there is a national annex at the end of their version of EN 206. In the UK, we have BS 8500. Annex M in EN 206 lists the clauses that permit these provisions. So 8500 itself is in two parts. Part one is the method for specifying and guidance for the specifier, and part two is specification for constituent materials in concrete. Now, we generally think of part one being aimed towards specifiers and part two being aimed towards producers. But in actual fact, these standards have to be read together, along with the EN 206, but they have to be read as a single document. And one of the reasons why we update these standards together. Theoretically, we could update part one and part two separately, but we don't because they are so interconnected. So just to run through quickly the main changes to the standards. I'll go into the detail behind these a little more later. But we've included BSEN 197 Part 5 cements and their equivalent combinations as general purpose cements. We've introduced a new concept of combined performance category for cements, and this categorises cements by their resistance to sulfate attack and chloride ingress. We've removed the minimum cement content water cement ratio as limiting values for resistance to corrosion of reinforcement due to carbonation. And we've removed characteristic strength as limiting value for resistance to corrosion of reinforcement due to chloride ingress. Table A6 is completely revised, and this is to allow the easier specification of the increased number of cements and combinations that we now have within the standard. We have improved guidance on identity testing and a change to the identity testing strength criteria for lower strength concretes. We have improved guidance on consistence retention, introduction to the concept of digital monitoring and measurement, and guidance to indicative strengths achieved from cements and combinations at different water cement ratios and cement contents. In part two, there are fewer changes in part two, although the editing work for this was actually fairly significant. So once again, we've included the BSEN 197 Part 5 cements as general purpose cements in Table 1. We've redefined the definition of a production day for air-entrained concrete. This was the main change, although the wording itself hasn't changed particularly, but there are clauses for production, delivery, conformity requirements have all been moved to a new normative annex. There's amendment for the combination conformity procedures for the new equivalent combinations, and there are corrections and minor clarifications. So just look at some of these in a little more detail. Identity criteria for compressive strengths defined in EN 206 Table B1 Criterion 2, as most people will be familiar with, is FCK-4. And this certainly makes perfect sense for normal strength concretes and certainly higher strength concretes as strength increases. But where it doesn't make a lot of sense is low strength concrete, where we have that criterion of -4 for C810. So you'd only be required to have a strength of 6 MPa on a C810 concrete. So what we've done is we've aligned the requirement in table B7 with BSCN 13791. So we now have for C810 concretes and below FCK -1, for C1215 FCK -2, and C1620 FCK -3. For concretes that are C2025 and above, the criterion FCK -4 remains. We're seeing, certainly concrete suppliers are seeing, increased requirement for consistent retention of concrete, where we have the requirement for concrete to remain live and open for up to several hours after production. And so the guidance has been improved slightly. The definition is pretty much the same. We've instead of saying specified time, we've said specified time period, and that's because there are pedants out there that if you say specify a time, they will say 12 o'clock and not 2 hours. The main change, though, is in the note, and this allows the specification of consistent retention to be from the time of loading, the time of arrival on site, or the time of final placement in works. So you can define this depending on the use of concrete, depending on what the specifier needs. Digital monitoring and measurement of fresh concrete properties. This has certainly been in a lot on LinkedIn recently with the requirement on HS2 for these systems to be fitted by trucks, but these are the real-time measurement and recording of fresh concrete properties, such as temperature, air content, consistency, and so on, by the delivery vehicle. Now, when this was written probably 2 years ago, we were introducing this concept as an idea that it may start to replace identity testing, not realising that actually contracts such as HS2 would start to use it before we would actually publish the standard. Now, this is a new table. This is in Annex C of Part 1, and this is to give indicative strengths of concrete. Now, this is a consequence, well, it's because of unintended consequences that we've had to include this. Going back to many years when concrete started to be specified by limiting values, it was generally agreed that for a cement type, water-cement ratio was the controlling factor for durability. But at that time, it was a requirement for the site to show compliance to the specification. We didn't use conformity then. And water-cement ratio is a very difficult thing to show on site, compliance to water-cement ratio. So included within these limiting values was then a minimum cement content. Because obviously if the concrete's batched at that minimum cement content and the concrete arrives on site at the right slump, your water-cement ratio is probably going to be about right. A thorough control of compressive strength was also then added. So that gave you an indication that the quality of the materials were about right. So we had 28-day strengths and we had slump test on site, and you could probably gauge that the concrete was correct. And this really was at a time as well when plants were manually batched. We didn't have autographic records to be able to look and see what was produced. All records were manual. So because this relationship between water cement ratio, minimum cement content, and characteristic strength no longer necessarily holds for lower strength concretes produced with lower clinker cements, the committee decided to try and decouple these requirements, which is absolutely fine. But what we didn't realise when we presented this to structural engineers at the Concrete Centre was that in fact engineers have been using these tables to give them indicative strengths of concrete as the basis of design. They could look at these tables and they could decide a cover, possibly for fire resistance, look at the exposure class, and determine what concrete they were likely to use to begin the design itself. One of my colleagues said it was a joke, but I think there's probably an element of truth in it, that in fact structural engineers buy BS 8500, tear out Annex A and throw the rest in the bin. That is how they use it. So to get around this and to give engineers some sort of guidance as to the likely strengths they can expect from these concretes, we've included table C1. Now, you'll probably look at that, and certainly concrete producers here will look at that and say, well, with my materials, I can get strengths far in excess of these. And that's probably correct. But this is guidance for the UK, where not all materials are limestone, and you know, we're having to deal with gravels and so on. Now, production day for air content, this has been relaxed. We've had for many years a requirement where we test, take an air test, 1 every 50 cubic metres, or when we have a cumulative supply of 50 cubic metres, which is far more onerous than any other requirements for testing concrete. So this has been relaxed to 1 per 150 cubic metres. Although if there is a non-conformity or you're going through initial production, then the test will be 1 per 50 cube. Interestingly, I was presenting on this the other day, and one concrete supplier said, I will not be telling my technicians this. Their technicians will remain at 1, or will think it's still 1 test per 50. I said, looking now at part 2, we've moved all the clauses for production, transport, delivery, conformity testing and conformity criteria. They were originally, in the previous versions of this standard, all were held within the main body of the standard. And as was pointed out quite rightly, they probably shouldn't be there. And so they've been moved. Now, it's a minor thing to say, but actually moving several clauses and putting them in an annex, you have to change all the references throughout the standard. This also has a knock-on effect that what was Annex A becomes Annex B, what was B becomes C, and so on. And so there's a huge amount of editorial work that goes on with a relatively small change. So moving on to Annex B, so this was previously Annex A. This is the conformity procedure for combinations. This annex, it's been revised to define the limits of proportion for ternary combinations now. So we can use combinations of Portland cement and 2 additions. And this generally follows the EN 206 equivalent performance of combinations concept. It defines which additions can be added, and for that combination to count fully towards the cement content and the water-cement ratio. Likewise, Annex D, which gives examples of how to apply that conformity procedure, have been updated for the use of the ternary combinations with Portland limestone cement with fly ash, Portland cement with GGBS, and then also to add additional limestone fines. So, just moving on to the lower carbon multi-component cements that we have included within the standard. I think most people will be familiar with this graph. It's from the MPA's UK Concrete Cement Industry Roadmap to Beyond Net Zero. And really we're looking at the third lever here. We're looking at the reduction of 12% through use of lower carbon cements and concretes. This requirement, or the need for these materials, is also accepted in the low carbon concrete route map. But if anybody hasn't read these, they're both free to download from these websites and give some really good information on producing lower carbon concretes. So, to understand what we're doing to produce these materials, we have to understand what additions are. In basic terms, they're powders that are added to concrete to modify its properties. We have inert materials, such as pigments and limestone fines when they're used as fillers. And we have cementitious materials, which are counting towards free water-cement ratio and binder content. And these could be limestone fines, silica fume, GGBS, fly ash, natural calcined pozzolana. We regularly use alternate names for these. We call them cement replacements, we call them supplementary cement materials, and so on. And these generally accepted that they increase durability, lower the heat of hydration, and give us strength gain beyond 28 days. So looking at this table's taken from the MPA's specifying sustainable concrete. The table's a little bit out of date because you can see in this table the embodied carbon of Portland cement, SEM1, is 860, whereas the latest figure that we have from the industry EPD is now 840. But this demonstrates the point I'm going to make regarding lower carbon cements. In general terms, the greater the proportion of additions that we use, the lower the embodied CO2. But the other thing that we can see from this is that similar proportions of additions results in similar embodied CO2. So because there's such a huge difference between the embodied carbon of additions and SEM 1, it doesn't really matter which one you use. What matters is the proportion that you're using. Now, as SEM 1 decarbonises, that will become more important, but at the moment, really we were looking for is to get as a greater proportion of additions in concrete as possible. And so, as I say, to reduce embodied carbon of concrete, it's quite simple. We reduce the total binder content, and we need to reduce the proportion of SEM 1. So the common cements that are in BS 8500 are BSEN 197 Part 1, 2011 cements. They've been in the standard for many years. And the new BSEN 197 Part 5, 2021 cements. And these are both composite cements, SEM 2CM and SEM 6. So what composite cements are is, I think we'd be familiar with a concrete which contains only Portland cement. And within the UK, we're certainly familiar with binary cements, where we're using SEM 1 and GGBS in combination. The new composite cements contain three materials. So in this example, we have SEM 1 GGBS and limestone, but it could be SEM 1 PFA and limestone, or SEM 1 GGBS and PFA. These are the composite cements. So the MPA commissioned a 2-year study into 25 of these combinations with the research work carried out by BRE, and they looked at dimensional stability, carbonation, sulfate resistance, compressive strength, chloride migration, freeze-thaw resistance, and alkali-silica reaction. And the outcome of that was that it was clear to see that optimization of cement powder components improves material efficiency. I'll explain that a little more in a moment. That we saw performance benefits with up to 15% limestone fines, and that multi-component cements and combinations were validated as general purpose cements for use in exposure classes XC, XS, XD, XF, and in DC classes. So considering material efficiency, we have a typical cement, SEM 3A, containing 55% Portland cement clinker and 45% GGBS. If we compare that to a multi-component cement, in this case 1, the clinker proportions remain the same at 55%, but we've replaced 15% of the GGBS with limestone fines. So that concrete, that cement, would have very similar embodied CO2 to the binary combination, because as I said earlier, it doesn't really matter which addition you use if the proportion is the same. So we've still got 45% of additions in that concrete, we've kept the clinker proportion the same. In multi-component cement 2, we've reduced the clinker proportion and we've reduced the GGBS proportion. So we've saved some clinker. We've also reduced our usage on GGBS that can be used in a second concrete to reduce the embodied carbon of that. But the key point here, that although we've done that, the strength performance of these three cements are similar. There's no change. So we've actually reduced embodied carbon, we've saved a material which has constrained resource and produced a concrete of the same strength. And the outcome of that is, if we look at the embodied carbon of these cements, these are just estimated from MPA fact sheet 18, is that you can see at the far end, the SEM 6 SLs are 60% lower than SEM 1, which is interesting. We can see SEM 3 about a third of the way along from the right, and we can see how that compares. But for me, the really interesting part is actually over on this side of the graph. It's as we start to introduce Portland limestone cements, SEM 2 AMs, SEM 2 BMs, where we're producing concretes that have similar performance to SEM 1, so at lower addition levels, but replace SEM 1 in use in construction, is where we'll see one of the largest benefits for lowering embodied CO2. Now, to understand the standard, we actually need to start understanding cement nomenclature. We're very familiar with using terms like SEM 1, SEM 2 BV, and C3A, but without really understanding what they mean. But with the increase in the cements, the numbers of cements available, and what can be specified, we have to understand the terminology. So, cements themselves are always factory produced. A cement is made at a cement works. It contains Portland cement clinker or Portland cement clinker with greater than or equal to 6% of other constituents. So it could be GGBS, fly ash, limestone fines, microsilica, and so on. And each has a letter. These cements are always denoted SEM. So SEM 1 contains greater than or equal to 95% Portland cement clinker. SEM 2 can be A, B or C. All that letter is doing after the forward slash is telling you the proportion. So SEM 2A has between 6 and 20% of additions. B, 21 and 35, and C, 36 and 50. And then there's a hyphen, and there will be the additional component that tells you what that material is. So, for example, we could have SEM 2AL, which is Portland limestone cement, or SEM 2BL, Portland limestone cement, SEM 2AV, or SEM 2BV. The composite cements, the multi-component cements, can be A, B, or C, and will be also denoted M, that tells us it's multi-component. And in parenthesis, we will have the two components, the two additions listed, with the one in the greater proportion being A1. So, SEM 2BM SL cements, it's a type 2 cement. We can see from the B that it contains between 21 and 35% additions. It's multi-component composite cement, and the additions are GGBS and limestone fines, with GGBS being in the greater proportion. Other examples would be SEM 2AMLS, which once again type 2 cement, with A being the proportions 6 to 20, and limestone fines GGBS, with limestone fines being the greater of the two. And SEM 2BM SV, we can see it would have 21 to 35% additions with GGBS and fly ash. This table is taken from a publication. It's not been published yet, but the MPA is publishing a How to Specify Concrete to BS 8500. It should be out next week. And what we've done is we've tabulated these cements just to make it a little bit easier to see how they fit together. Now, it's worth noting that on here we have SEM 5, which is not in BS 8500, but it would seem daft to leave it out when you're producing a table to show how they all fit together. So it's all in this table here. Now, in the UK, we tend not to purchase cements anyway that contain multi-component additions. We use what are called equivalent combinations. So combinations are produced from a cement and one or more additions in the concrete mixer at the concrete plant. But these will conform to the requirements of EN 197 Part 1 or 197 Part 5. By using the conformity procedure, the limits of these proportions will count fully towards the cement content and the water-cement ratio. Now, combinations are not called SEM, they're just denoted C. So a SEM 3A cement, when it's a combination, will be C3A. A SEM 2 CM SL, when it's a combination, so produced at the concrete plant, will be C2C SL. So looking at how we convert them, so for example, here's a cement, SEM 2BS. We can see it's type 2 cement, 21 to 35% additions, and that addition is GGBS. For this to be a combination, it becomes a C2. We remove the forward slash and just use the B so we know the proportions. And we have, and we have the S. So the SEM 2BS becomes C2BS. A slightly more complicated cement, SEM 2CMVL, becomes C2. We lose the forward slash, it just becomes C. And we don't need the M. We can see there are two additions from the letters, so it is redundant. So a SEM 2 forward slash C-M-V-L becomes C2CVL when we make them in the concrete plant. So in 8500, we've introduced these new cements. The first four, the SEM 2 AM and SEM 2 BM cements, were in the previous edition of the standard, but not really used, because we're used to using binary combinations of SEM 1 and GGBS up to 60-odd%. So we didn't have multi-component equivalents to those cements. With the introduction of the 197 Part 5 cements, we can now replace up to 65% of the cement with other materials, and so we have equivalents to those binary combinations. So as well as combinations of Portland cement, GGBS and limestone, we also introduced Portland cement, fly ash and limestone, and Portland cement, fly ash and GGBS. So how does this look actually when we're producing these combinations of the plant? So a traditional 2-silo plant that we would have fairly regularly throughout the UK, would purchase SEM1 from a cement works and combine it with GGBS. And by doing that in varying proportions, we could produce these cement types, these combination types, sorry. But in general, the main two supplied were SEM1 and C3A. Now, if instead of using, because of the new cement types allowed in the standard, we purchase SEM2AL instead of Portland cement and combine that with GGBS at varying proportions, we can end up with these cement types. There's far more, with probably the common ones being SEM2AL, so Portland limestone cement, and C2CSL and C6SL being general replacements to C3A. Where it gets complicated is if you have three silos, because when we have 3 silos, we can produce this list of cements, depending on your proportion. Now, it would be likely that the ones that you would actually see within the market are those highlighted. But you can see how why we need to understand cement nomenclature when we're producing potentially a huge number of cements. One thing that was noted in the process, and quite late on in the process, because obviously when writing the standard, we don't really understand entirely how the market will implement what we're doing. It was noted that where you have a 2-silo solution, so we're purchasing SEM2AL and GGBS, for example, that where that SEM2AL is a direct replacement to SEM1, it may not have a particularly high proportion of limestone fines. And as we combine that with GGBS, the proportion of limestone fines dilutes very quickly. And so this would be definitely of benefit to the cement producer, because the cement producer is decarbonising by supplying Portland limestone cement instead of SEM1. But it doesn't actually produce the optimised lowest carbon concrete. So what the standard allows is for the producer to add additional limestone fines to top that up again. And so the cement producer will get the benefit of producing cements which are lower embodied carbon, and the concrete producer can then optimise mixed designs to produce the lowest carbon material that they can. So, just moving on to specification of concrete itself. So this hasn't changed. We still specify concrete to prescribed limiting values. So by strength, minimum cement content, and maximum water cement ratio. And we say that if those limiting values are met, performance is assumed. So the engineer specified a cover, a normal cover, an exposure class. So we have a cement type, and if we meet those limiting values, we are deemed to satisfy the requirements of that structure, and it will hopefully last its design life. But this is one of the reasons why EN 206, the European standard, is non-harmonised, is that deciding limiting values of strength, minimum cement content, and water cement ratio for all materials across Europe in all exposure conditions, whether or not it's in Norway and whether or not it's south of France, is almost impossible. And so we have the UK values for these. And you could actually say that these are possibly conservative, because concrete in the north of Scotland is not necessarily has the same requirements as concrete in the south of England, but we use a UK-wide figure. And so, if we're looking at these limiting values, this is from the previous version of the standard. We can see you would select, for example, XD3. The cover isn't on here because that was at the top of the page of this graph, but that would be probably a nominal cover of 45 millimetres. And you could look at the available cement types and generate your limiting values. So C3540, minimum 380, 0.4. Likewise, if we're looking at DC classes, so there's no cover here because we don't consider that for sulfate attack, but we have our cement types that we can look at, and we can determine, based on our DC class, the limiting values. The problem that we have is that with a revision to the standard, is there are now 81 cements and their equivalent combinations that we have to fit into these tables somehow and still make the tables usable. So what we did was, first of all, looking at sulfate attack. This is just one example of the BR report. This is a 72CmVl cement, which is in a class 5 solution at 5 degrees centigrade for 2 years. We're able to categorize these materials against control. So in this case, the control is a fly ash cement, 30% fly ash. And we did it both at DC2 and DC4 nominal specifications, because there was concern, and as you can see, that it's a good example on these cubes here, that some of the cements at 380.35, there might not be sufficient differentiation between them to be able to categorize them. And so we put them in, you'd never expect a DC2 specification to survive class 5 sulfates, but it gives us an indication. But as you can see here, the 72CmVl performed very well indeed in these highly aggressive sulfate conditions. And so that allowed us to group all the cements, A to G, to align with BRE Special Digest 1. So that keeps BRE Special Digest 1 as a relevant and up-to-date document. The tables and cement types in that document might not be up to date, but as guidance for use of that document in sulfate conditions, it's still correct. Likewise, for chlorides, mean chloride migration coefficients were looked at for all the cement types, and these were grouped by designation 1 to 4, generally to align with Concrete Society Technical Report 61. So these were combined into an alphanumeric categorization called the Combined Performance category, and all the cements were listed in Table A6. This Table 6 here is once again from the how-to guide that we'll hopefully publish next week, and just gives the combined performance categories of some of these cements. But if we actually look at the top of Table A6 in 8500, you can see why we had to categorize these and not list all the cements. So this is just some of the cements that sit currently within A1 category. What this allows us to do, though, is if we take, for example, sulfate attack, and we look at the previous version of the standard, the way that it looks now is it's far simplified. We have also, you can simply refer to the combined performance category, and you can look at Table A6 and determine which cements fit within that category. Likewise, for resistance to chloride-induced corrosion, this was the previous version of the table. We now have this limited amount of information that you can simply refer to. Now, the other thing to note in here is that it was decided that strength was no longer required as a limiting value for these. And in fact, it could be problematic, because obviously some of these lower clinker cements may not have particularly good characteristic strength. And if you put a limiting value of strength in there, you're precluding their use for no particular reason, when really the performance is being driven mainly by water-cement ratio and maybe partially something to do with the total binder content. But that's been removed. And just moving on to the final part of this, which is carbonation. If we look at the previous table, in previous version of the standard, all cements were allowed apart from the Type 4 cements, where they had a slightly different designation. Now, what was found through the trial work was that certainly some of the lower clinker cements had quite high carbonation rates. And so there was a lot of discussion within the committee as whether or not they should have a different designation to show that they carbonated rapidly. And then there was concern that actually if we highlight that some cements carbonate rapidly, there would be people who would specify them for that very purpose and say, hang on a second, we have a low clinker, low carbon cement, and it absorbs CO2 rapidly. This must be a good thing, which could be problematic. So this table became very difficult to produce, trying to fit the cements all into this table. But what was noted, this was noted by BRE, but had been noted by others previously, is that there was a relationship between compressive strength and carbonation depth for all cements, and also held for carbonation rate. And what this allowed us to do is move more towards in some ways it's a performance specification, where we can use strength as a proxy for carbonation resistance. This far simplifies specifying these new lower clinker cements, because they're simply being controlled by strength. So the table now, as I say, we're able to use all cements and only specify by characteristic strength. Now, the thing to note with this is that actually for a particular strength, for XC34, cover depth has increased slightly. It's just something to notice. But I think it's particularly important, certainly as you move towards lower cover depths, that we have adequate strength to be able to provide adequate carbonation resistance. Okay, and I think that's it for me.